Now we want to look at what we call projectile motion. And the idea here is that we're going to not just deal with something moving in a straight line, which is what all our motion in our course has been about so far. But now we want to deal with a particle that's moving in two dimensions. So it moves with horizontal and vertical velocity. And so we get a particle that's moving, and it's going to move in this type of shape. Now, our aim with these ones is to get equations of the motion that exist both horizontally and vertically. But then we can also link it back up to our Cartesian plane and put it in terms of x and y. For something to be moving in this type of motion, what it needs? Well, it needs some sort of velocity to be starting off with. It needs some sort of angle, obviously, that it needs to be projected at. So that all's going to come into play to find these motions. Because really, the only thing we know for sure when we start off is a situation that only gravity's acting on that. And that means there's no acceleration horizontally. So once the particle's projected at a velocity v and at an angle of theta, then there's no other acceleration happening except for the gravity that's going to pull it downwards. So that's where we have our starting positions. So the second derivative of our horizontal motion is equal to 0. Our second derivative of our vertical motion is equal to minus g, where g represents gravity. So acceleration horizontally, acceleration vertically. And we also have this idea that our velocity diagram can be drawn up and we can get these relationships. So the velocity, it's launched at a certain velocity at a particular angle, but we do have a horizontal velocity and we do have a vertical velocity, and it may be working in one of two directions there. So the velocity may be moving up or it may be moving down depending on the situation we've got. So that's what we've got with our velocity and diagram there and the relationships that exist. So how does that help us get our horizontal motion? Well, we start with our acceleration being equal to 0. If we go to get our velocity from that, we're going to get just a constant. Now we know initially dx dt is going to be equal to v cos theta, because cos theta here is equal to dx dt, so the horizontal velocity over the total velocity of the particle. So we can write dx dt is equal to v cos theta. So that's where our constant starts to be, v cos theta. And then we integrate that again, we get v cos theta times t, because it's just a constant being multiplied by t there. And we get a second constant of integration. And then we know that when t is equal to 0, we're starting at the point 0, 0. So there's no actual horizontal value, so it's 0 there, so our constant with 0, so we can get our expression there of vt cos theta. Now, because it's not always going to start at 0, and because it's going to have different starting points along the axis here and moving, we start all the time from this point and move to get our position going through these steps. So do that all the time, unless you're actually given them in a question, then you don't have to do it. But we want to set that up all the time, so we're making sure we get the correct constants every time. So, and hopefully this is making sense to you, because if you're moving horizontally here, really it's just whatever the speed was horizontally that we've got times time. That would give us our position, because there's nothing else affecting it. So what about our vertical motion? We said the only force acting upon the particle once it's been launched is gravity. So the particle's been launched, and so we get gravity, and it's because we're taking velocity being moved in the forward direction there, velocity acceleration is going to be negative. It's going to be acting in a negative direction. So we're going to have minus g. So to get our velocity, we're going to integrate that function, and we get a minus gt. Again, we get a constant of integration. We go back to our triangle here, because we know that sine of theta here is equal to the vertical velocity over the velocity itself. So then we can say the vertical velocity would be equal to v sine theta. So that's where that v sine theta comes from this triangle. And so that's our when t was equal to 0, that's our velocity. So our constant ends up being that. So we get our statement for our vertical velocity. And then we integrate again. So we get to our function for the expression of the position of y. So again, we get t squared minus times divided by 2, or times the other half. Vt, so v sine theta gets multiplied just by t. We get a fourth constant, and we know we started at 0, 0. So when t is equal to 0, y was 0. So we're able to sub those in, and our constant there becomes 0 as well, because that would be 0, that would be 0, that's 0. So we get a fourth constant being 0. Now, again, don't take it for granted that that's going to be your expression for your motion every time. Because again, if that was starting up this point here and being projected, then the y wouldn't be 0 at times equal to 0. And we'd have a constant that shifted it up. So we got to be really careful. We set it up the same way every time. Start with minus g, integrate, get our constant of integration from our velocity statement, our velocity diagram there, and then integrate again once we've got our constant there, get our position statement, work out what our constant would be, and it just happens to be 0 in this case. Most cases it will be 0. It just depends on where the particle starts. If it starts there, it's going to be 0. If it moves up here somewhere, then that's going to give us a different one. So there we go. There's how we find our horizontal and vertical motion. Realize that because you've got functions in terms of x and t and y and t, then you can start to relate x and y together. So that will be part of some of the questions we'll see later on, and that's not too bad. So you can get a Cartesian equation for that motion as we go through. And as you're probably thinking, well, wait on, that might be a parabola because we've got a t squared. Yeah, you'll be probably right most of the time. So have a look through there. Be able to start with your accelerations, integrate to get your velocity and get your constants, and then integrate again to get your position and get your constants there.